Good morning. Vagan, can see it.
Good morning.
Morning.
Hello.
Hello, I can see your screen. Everything is okay.
Okay, so I can take it away.
Yes.
Vagan.
Hello.
Hi.
Hello.
Hello.
Looks like our bosses from China may not realize the time difference.
Hi, Vagan. I don't know, but if you want, we can try to share the screen. I mean, the speaker can try the screen sharing before the arrival of the two session chairs. Okay, Vagan is okay. I can see it. Okay, okay. And Johannes, okay, okay, I can see it. Perfect. Thank you. And Christian Zehetner. Oh, perfect, perfect. Thank you. I can see it. Perfect. John Angelopoulos.
Good morning.
Morning. Can you share your screen, please?
Let me see.
Yes.
I think I'm sharing now.
Not yet. Okay, now it's okay. Perfect. Thank you.
Okay.
Okay, all the speakers are here and everything is okay. The with the screen, but we are waiting for the session chairs. Then you can wait.
I believe in the worst case we can succeed even without bosses.
Yeah. Okay, I can replace the session chairs who are missing. I'm the assistant. I think that in 2 minutes we can start the session. Okay.
Yes, of course.
Okay, perfect.
The show must go on.
Yeah. Absolutely.
The show will go on. Thank you.
Yeah. Okay, it's 9 o'clock. Then I think we can start. I'm Vittorio Solina. I'm the session I'm the assistant of this session, but I will replace the session chairs who are missing, Fei Tao and Kinglin Kid. And welcome to this session, Digital Twin-Driven Smart Manufacturing. We can start with the first speaker, who is Vagan Terziyan, with the paper Towards Digital Cognitive Clones for the Decision Makers, Adversarial Training Experiments. Please, the floor is yours.
Hello, everybody. Just check if my screen is available.
Yes, perfect. I can see it.
Okay. So, as I already said in previous sections, I represent University of Jyväskylä, Finland here, and also our partner university in Ukraine from Kharkiv. So this is our team on the screen. So it's me, designed by artificial neural network, and my colleagues, Professor Turin and Maria Svetlana from Ukraine. So first, I just remind what is our view to Industry 4.0. We consider Industry 4.0 as a combination of very flexible infrastructure, where we have various kind of system of cyber physical systems connected together. And we believe that this kind of system is controlled by so-called collective intelligence. It's a combination of human control and artificial intelligence control, or artificial agents. And we also believe that these kind of control points can be controlled not only by humans, but also by artificial autonomous digital cognitive clones of humans. And we, for purpose, use the word clone instead of twin, just meaning that twin is something without soul, and clone is something that we are copying not only just functionality, but also some properties of a mind, and it's autonomous and proactive. And this one of the scenarios we have been using with our partners, where we believe that such kind of digital twins of humans can be useful from both sides, from the sides of which represent the industry as such. So digital, different persons who represent critical decision points of this flexible process, and they can be replaced with digital cognitive clones, which can make these decisions instead of people and the same way as these people would do if they are here. And also represent customers on the right side. And these customers can be also represented by digital clones, and in this case, company can adapt its processes to meet expectations of customers. So from the early stages of production to the later various kind of business processes. And so because of that, we need to support this kind of technology for actually cloning both customers and digital workers, making them proactive, agent-driven, and enable them together with their human donors and other humans as a collective intelligence. So consider this important concepts that we are using in this view. So we have humans. Let's say it's me as an example here. So we have agents. We know it's a kind of autonomous, proactive software entity capable to perform goal-driven behavior. And some kind of functionality. It can be capability, which can be hardware, software, anything can provide certain functionality or certain capability. So when we are talking about cognitive cloning of humans, how actually we are talking, it must involve cognitive cloning of particular capabilities of a human, at least those which are important in the decisions that humans are made. And why we need agent? Because we need this kind of capability to be proactive. Our first results were already this concept 17 years ago. We have such kind of projects where we designed special agents that used as a mediators between human and external capabilities. So it can be different kind of external service providers, including digital twins of various Internet of Things components. And if a human needs certain information from sensors of this real stuff, this kind of information goes through particular agents to the decision maker side. and vice versa if certain control would be needed over these pieces of hardware, then this process also goes via this kind of representative agent. So agents as a proxy, it's already designed, and we called this middleware as ubiquitous middleware or ubiware, and it was quite popular that time among our industrial partners. So these are, in this slide, there are references to these projects where we did ubiware, and later we did also ubiroad middleware for smart road environment, and the system of power lines of Finland is based on also this kind of agent-driven middleware. Then later we start to add to this technology something else. And this something else means that we realize that if a particular system or person, in this case person, doesn't have certain skills, just no time, for example, to learn Chinese language or to learn how to drive particular device or car or anything. So we start to think, so why not to make possibility that machine learning algorithm learns this skill as a kind of special capability. So we put this capability inside of agent as a driver of this capability. And we again create this kind of connection between human and this kind of trained skills. So we enhance a human with that kind of smart skills. And as I will later show that we are now using this as a part of our international master programs in the university, where we design such skills during the study of a human. So the thing that you cannot do during your studies, it can be automatically generated. And when you graduate together with such kind of smart agents in the pocket. And we call this technology as a cellular collective intelligence, where like you and also agents which enhance you. And also a certain environment which makes different cells to collaborate with each other via these agents. So this is another. To a certain extent is directly shown in this screen. So you can capture particular decision-making skill. So it's like simple, given a simple decision problem, and I train particular neural network using this person as a donor for supervised learning to put labels to particular samples. The neural network learns to make decisions similar to this person, and a set of decision problems together put inside this software agent, which actually represent me in such kind of situations where these particular decisions will be needed. So in this case, I have some guarantee that the decisions will be made exactly as I would be doing it in these cases. So why this technology is good? Because we have quite easily in digital world, I can make copies of the same agent and put it to many places of decision process. So in this case, I enhance skills of the same person. If he is good expert in certain decisions, so he can make these decisions simultaneously in many places. And also, we created it's our publication where we also create the way that such kind of skills can be, but it's your skills. So this kind of agent can be patented, and you can sell your skills to other companies, other processes. If they believe that you are a good expert in a particular place, then they can borrow your agent to represent you in this process for a certain fee. So we call this technology as a patented intelligence and publish it here. And briefly, why this kind of cloning, I mean, theoretically is possible in terms of machine learning. I will show some slides. So if we have a certain donor, let's say it's human, and we have to train particular clone of it, then we must have certain decision task. And consider that this is simple classification task. You have certain sample, well, like parameter of certain situation, and you need to say to which class this situation belongs. For example, go or not go decision, or yes or no decision. And in a very seldom cases, donor can explicitly say what is the decision boundary between go and no go, according to his own view. So if this is the case when explicit decision boundary is available, then this kind of cloning is easy. It's explicit transfer of knowledge between donor and the clone, and it can be done with simple, explainable artificial intelligence tools. But in many cases, this is not possible, and the only thing that what we can do with our donor is to ask to give different situation and see how the donor behaves, address this situation, and create some kind of training set of samples. And this decision boundary will be learned based on, for example, deep learning algorithm or deep neural networks. And this decision boundary will be learned by clone. So also interesting to see that different people are actually different because they put different decision boundaries. Of course, the clear cases, they classify similarly, but there are certain cases that different people classify differently. So therefore, we need such kind of technology which we based on the generative adversarial networks, where we try to generate various kind of samples close to the decision boundary, so that we really try to capture exact decision boundary for a particular person. So that we must guarantee that our clone is not only making the correct decision the same way as donor is making, but also incorrect. So mistakes must be also the same, because we call this intelligence also as responsible artificial intelligence, so that responsibilities clone also share together with its donor. So this is architecture of our generative adversarial network. So it's not classical architecture, because we have a special type of discriminator, so-called TURING discriminator. So we have various kind of reality samples coming to both trainer and trainee, to donor and the clone, and they are addressing this situation with a class label, and certain comparators see how close clone is making decisions as a donor. And if there is some kind of mismatch, then this neural network, which is our artificial clone, will be retrained all the time until we have very close decisions. So our idea is to make clone making decisions close to the donor. And later we, of course, put all these different decision tasks together. One, we connected with semantic graph, all these decisions. So it's details actually in different papers. So I just say, so that we have, of course, not just one decision, but many decisions connected as a semantic graph. In this particular paper, we train, we have a real industrial case. It's from our NATO SPS project, Cyber Defense for Intelligence Systems, and we have military logistics laboratory, where we have a certain camera watching on the process, and we try to train clones of operators watching on the process. And we, the training, our techniques actually show that our trained artificial classifiers, they are making decisions not that bad. It's almost the same as performance as the humans make, but also important point that the correlation between clones and the donors is very high, so that actually technology of cloning works here. And we try this environment in a business as usual process, just simple things are ongoing and a person is classifying and together with donor. But also we put it in a situation where we have attacks, so certain attacks where special poisoned images are given by hackers to fool the system. And in this case, we just check how the system is fooled or human is fooled, and we see who is more stable in this case. And in both cases scenario, we show that this kind of clones are very useful, especially when they make decisions together with the humans. So it's just a set of experiments where we show performance of our cloning technique. And also we make special type of content as a vaccine. It's digital vaccine that we add to our digital clones to be, how to say, stable in the cases of that adversarial attacks. So it's just immune system for our digital clones. So this is also works, and we have a special way to generate such kind of images. So coming to the end, I just said that we have launched also international master program in our university named Cognitive Computing and Collective Intelligence. And as I told you, it's the first university program for collective intelligence where humans learn together with their digital clones and autonomous digital assistants, so that every human, assume that student, when graduate, it has not just a certificate of master degree, but also set of artificial cognitive clones trained so that they can make or enhance capability of every student in the industry. So welcome to join this program. It will be soon next call. So thank you. That's everything I wanted to say today.
Okay, perfect. Thank you, Vagan. Very nice presentation, very interesting. Any questions from the audience? Questions? No? I have just one question. Can you tell us something about your future plans? Do you plan to apply this approach to a specific sector, to a case study in the future, I mean?
Yeah, we have several options here. So one, of course, is that make a really wide that digital cloning, which includes not just simple cognitive skills, but at least partially more complex mental skills, like making these kind of clones more human. And this is one direction that we are going to do. But also from application areas points of view, of course, cybersecurity is one of the places, because humans can be fooled by one way, by hackers, but their digital clones by another way. So we need to find special ways to create real immunity for our clones against cognitive hacking, we called this by this way. So there are many different things. The major thing is that as pandemic shows now, we all are under pressure that, okay, if something happens and you have to stay at home, would you lose your job? Can it be so that your digital clone, especially if you are making cognitive work, just normally, can your work can be done by your clone this time? So you are still in. So you feel that you are in, and the things which your clone is doing will be very similar to yours. Even erroneous behavior. It will be your behavior. So you just trust your clones in this case rather than human replacement. So this is also a possibility to temporarily replace humans in such kind of processes. Okay.
Okay, perfect. Thank you. Audience? No? Okay, thank you, Vagan, Terziyan. Very nice presentation, very interesting. Thank you so much. Well, we can move to the second paper, to the second speaker. The title of the paper is A Multi-Layer Architecture for Near Real-Time Collaboration During Distributed Modeling and Simulation of Cyber-Physical Systems. And the speaker is Johannes Schönböck. I think, I hope the pronunciation is right.
Sure.
Please, okay. Please, the floor is yours.
Yeah, thank you for the kind introduction. As you already said, my name is Johannes Schönböck. I'm a professor at the Austrian University of Applied Sciences here in Hagenberg. And I'm happy to present you the paper entitled A Multi-Layer Architecture for Near Real-Time Collaboration During Distributed Modeling and Simulation of Cyber-Physical Systems. So quite a long title, but hopefully I will explain it to you in the next few minutes. And this work was done together with many colleagues and is a joint cooperation between the campus here in Hagenberg and the campus in Wales. And this work was done during a research project called DISMOSIM, which is funded by the Austrian Research Promotion Agency. So what is our main motivation? We all know the vision of Industry 4.0 or 4.0, and the key vision thereof is to decompose complex processes into smaller ones and more manageable chunks. Tasks should then be maybe distributed across different machines or actors in a digitally connected world. Following this vision, we think there's a clear trend towards different forms of collaboration across companies, across teams. In our scenario, we deal with the modeling of cyber-physical systems by applying so-called multi-body simulation. The individual parts of these systems can be broken down into so-called modules, and the vision is that we provide an environment where you can individually model parts of the system, but in a collaborative way. E.g., one person models a motor of a car, another one models the tires, and finally you put them together into one common model, and we want to provide means to do this in a collaborative manner. To achieve this vision of virtual engineering, we think we must better support the engineers. So we believe that there is an increased demand for collaboration tools, and that's the main focus of this project. In this respect, we think that engineers need some kind of shared access via the internet to a cyber-physical system for collaborative modeling, simulation, and also result discussion. When we compare this vision to the current state of the art, we see that currently there are, at least we believe, some steps to go. Currently, a common situation is that modeling or the modeling process is currently done by a single user in a centralistic manner. So, for example, when modeling a motor of a vehicle, typically a single person models the whole system and all parts thereof. And of course, this might cause problems since he or she might not be expert in every single part of this cyber-physical system. So some sort of collaboration happens currently only in the sense that one modeler sends a model via email to another person or by using some kind of file sharing mechanisms. This is quite a cumbersome process and is also quite insecure. If we look at simulations of cyber-physical systems, it is also typically conducted on a single workstation. So there's hardly any parallelization, hardly any sharing between different workstations. And so this time-consuming task is done on a single machine. And last but not least, if we consider discussion of simulation results, it is most often the case that some screenshots are shared or shown, presented to the audience. But in general, this process of discussing simulation results is only very loosely coupled to the remaining process of the modeling and the simulation. So to summarize these problems, currently state-of-the-art, like programs known like Adams, which is the market leader, are quite desktop-oriented, workstation and single-user-oriented programs. And another problem which we identified is that simulation is currently rather strictly separated from real experiments with real hardware. So it is rather a cyber system, I say, than a cyber physical system. So what we want to achieve also in this project is a more integrated view. For example, in the simulation of a model, it should be possible to simply state whether a certain part of the model should be simulated by using mathematical equations, or if the data should be gathered by some real test hardware that is connected to the system. So our vision is that everything is distributed, and we want to provide an modeling environment which allows to model and to simulate these cyber physical systems in a collaborative manner. And the project is called DISMOSIM, which is short for Distributed Modeling and Simulation. So we want to provide a team-oriented and collaborative view on the design and simulations of these systems, and also the hardware should be seamlessly integrated into this environment. We also do not want to restrict users to a certain device. So in general, we want to allow the users to use their laptop, their PC, but also their smartphones for certain situations, or even large screens like, for example, a Microsoft Surface Hub. Powerful workstations should be used to calculate simulations together, so it should be somehow distributed in a network. So this is the main vision. And from this vision, we derived some design goals. Yeah, our vision is to provide some kind of virtual workshop. A virtual workshop is more or less a workspace where multiple engineers can collaborate together, where they can share their work and can jointly model a cyber physical system. So these workspaces should allow for hybrid collaboration. The term hybrid means it's not relevant whether people work on the same site, on the same place, we call it co-located, or if they work remotely, so at different locations and even with different devices. So a really hybrid setting. Access to this workspace, as I already said, should be in general device agnostic, meaning we want to make use of certain advantages and avoid disadvantages of certain technologies. And crucial in this whole setting is communication. We need to achieve near real-time communication. On the one hand, it is required for group awareness, so immediate synchronization, for example, of the 3D workspace or virtual cameras, and so on. And on the other hand, we also have time-critical synchronous simulation tasks, like this interactive kinematics solver or simulation I will show you in a minute. So in general, sim as some kind of network with different nodes in it. these different nodes are, on the one hand, can be seen as hardware where different services can be placed on it. So for example, a laptop or a quite powerful laptop may provide means to model the whole system, may provide means to at least start or stop some simulation runs, and may, for example, provide means to visualize results of a simulation. When we consider, for example, a smartphone, on the other hand, it might not be that useful to provide a 3D modeling environment on a smartphone. This would be quite cumbersome. So we left this service out on smartphones. But of course, you can at least provide some limited or some restricted views on visualizations of results. And maybe very useful, you can start or stop a simulation on your mobile phone while you are in the train or on a business travel. So this is quite useful. And finally, we provide large or services on large touch walls like the Microsoft Surface Hub. Again, here you can make use of all the services that are available or that we provide. And for example, another feature here is that you can use your mobile phone or your iPad, for example, to interact with the large Surface Hub. So for example, if you are in a co-located scenario, it's not that convenient if too much people stand directly in front of the large touch wall. In this case, it might be more convenient to use your mobile phone to interact with this large display. So these are, on the one hand, nodes that provides UI, and all together, well, the thing around it is that we provide means for collaboration between these nodes. And on the other hand, we have also services that work without any user interface. Most important, we provide two different kinds of simulation servers. A so-called dynamic solver is used for precise but also very time-consuming calculations of simulation runs. And these results are then used in the visualization services on the UI node to discuss the results. On the other hand, the kinematics simulation server is much less precise, but on the other hand, much faster. And so we are able to provide instant feedback on the UI nodes. And this feature or this service can be used, for example, rapid testing of your models. I will show you this feature in a minute. And finally, we also provide means to integrate real hardware, as I already told, and which is a point of future work still, is the integration also of software in the loop, testing or simulation. Software in the loop simulation is used to describe some kind of test methodology where executable code, for example, code of a controller strategy, can be integrated into this whole environment. To establish this network, we base on a simple three-layered architecture. At the lowest level, we have the network layer. As the name might imply, this layer is responsible to transfer the data between the nodes in near real time. We base on common web standards and web protocol, more precisely on WebSockets, since they are quite fast, and we achieve our goals with this standard protocol. And on the other hand, we rely on the so-called distributed data protocol of the Meteor framework. And Meteor is a standard web framework which provides very nice means to solve the complex synchronization problems if you have more than one person or workspace that models or changes something on your data. The task of the model layer is on the one hand to provide means for administration of the virtual workshop. So for example, register users, provide access to a workspace and so on. And more important, it provides a common data model to provide means to model a multi-body systems. For example, here you can see this object collection, and within this collection, you can see those bodies or those objects we provide. A rigid body is the main thing of the whole, and then you can model forces, constraints, measures, and so on. Yeah, and furthermore, you can add visuals to your objects. So, for example, a 3D visualization or some basic symbols. And finally, the service layer provides all those services I mentioned before. For example, means for 3D modeling, means for collaboration, and so on. And of course, the services depend on the functionality and the device you use. So not every service is capable to run on every device. So I hope you can at least get an impression of these figures. This is the current deployment we have. I do not want to go into too much detail of this, but you can simply use services, deploy them on different kind of nodes, and yeah, so you can basically integrate a new node or new services in your network. And in the following, I want to present some services in more detail. So the main feature, of course, is collaboration for team-oriented modeling of cyber physical systems. So multiple teams at multiple locations are connected via internet. You can use your different devices, and we allow for a team-oriented modeling of cyber physical systems. So typical scenarios could be some kind of meeting where you may be co-located, or also you can join remotely. Home office is common nowadays, is supported with this project, or working on business travels, or also enabling some kind of training scenarios or teaching where you can share or where you can participate in a collaborative workspace. So I hope you can now see this video. It gives you an impression of the collaboration feature. So you can see one person, for example, is moving this piston of this crankshaft, and you see it's instantly synchronized with the view of another user. Now they are standing in the same room, but of course this can be done completely remotely. And for remote work, we also integrated a video conferencing software. In our case, we used Jitsi, which is free and can be integrated. So we provide also all means of video conferencing tools, and maybe I think it's at the beginning. Yeah, you see this gray shadow here. This, for example, is used to show where your partners are looking. You can follow a partner to see where he or she is working and which part he or she is modeling. Concerning this kinematics simulation, or this rapid assembling and testing, the scenarios that you have commonly or like to commonly assemble some subsystems stemming from different suppliers or different organizations. So in this example, the shovel of the excavator could be modeled by one company, and the body of the excavator could be modeled by another company. And now you want to put them together in an interactive way, in a common way, and also want to see, okay, does the shovel fit to the body of the excavator, for example? And for this, we provide a means for fast kinematic testing. So you can use, for example, touch gestures like it's shown here, and move, for example, the shovel of your excavator. So if we look at this video, two persons can jointly model, and by simply using touch gestures, you can somehow check if all constraints are valid. Or another example, again, this crankshaft. Yeah, you can now test if you have attached all conrods, all pistons correctly. Yeah, and during modeling, you can do quite a rapid, rough testing to get an impression if you did right. And on the one hand, and on the other hand, it can also be useful to for some kind of debugging or to find errors. And here you get at least an impression on the integration of mobile phones. So on the one hand, in this picture, the mobile phone can be used to interact with the large screens. So for example, it is possible to use the gyroscope to rotate 3D model elements to at least roughly get the right position. Of course, you have to correct this then by using again some forms to edit these values, but to get a rough expression, you could use this gyroscope. And on the other hand, here you see a screenshot of our mobile app. For example, you can trigger a new simulation run, stop simulation run, change simple parameters of your simulation run. So yeah, well, you get the notification when the simulation has finished so that you can easily check your work while you're on the road. Yeah, and finally, the integration of hardware. With Dismosim, we are able to integrate decentralized real-world components. So the user can select whether the simulation should be conducted on the basis of a numerical calculation. So when modeling, for example, he or she simply clicks on this part of the model and can then choose whether it's really a cyber element or if it's a physical element. So if you have some hardware available, and we provide protocols, and if this hardware has some internet access and can send data via internet, we are able to integrate these data gathered by the hardware. Yeah, so that was the main vision and the current status of our projects. Of course, there's a lot of future work to do. Maybe I'll start with the last point. The next step we will do is to go into the field and make some user studies to test our collaboration features and to test this kinematic solver I showed you. Another current open point is the integration of the software in the loop testing. And two other things, currently our solvers still run on one single powerful workstation. We want to investigate on things like parallelization thereof, using cloud infrastructure, cloud services, and so on. And a more futuristic future work, I would say, is the integration of VR and AR, also augmented reality services. So VR could be used to really provide more natural models so that you can really model in a 3D environment. Augmented reality, on the other hand, could be used to, for example, display simulation results directly on real hardware. So for example, you could create some heat maps showing mechanical strength and you directly augment this on the real test hardware you used. So I want to thank you for your attention, and of course I'm happy to answer your questions.
Thank you, Johannes. Very nice presentation. I really liked it because I think this architecture is extremely useful and makes collaboration easier, especially in this pandemic time. Any questions from the audience? Yes, I can see many hands. I don't know the order, but I see Martin Steiner, Joseph Waltman, and Stefan Ben. And please, Martin Steiner. It is the first I see in the,
yeah.
in the list. Okay.
Hello, Steiner Martin, TÜV Austria. I have one question concerning the hardware. For example, a team working together and controlling the hardware like seen on the picture, and I don't know, two virtual connected and one is on site, and one puts, for example, the finger in a position where he shouldn't do it, and the other one is controlling the device and he gets injured. Are there any ideas of safety concerning controlling hardware from a place where you don't see it, for example?
Yeah, this is a good question. We are currently at the very beginning of this hardware in the loop integration. Of course, this is critical. This one hand, or at least one thing could be to use, for example, augmented reality or some kind of remote views that you get an impression what's happening on this maybe remote hardware. But I have to say I'm the expert at this user interface and programming part. Our colleagues in Wales are at the campus in Wales are more dealing with this all mathematical and hardware stuff. But as far as I know, this is currently a topic that they are heavily discussing, how to somehow constrain these simulations that you don't run in any critical situations. But yes, that's true. That's a critical point.
Okay, thank you.
Okay, perfect. And then I see Joseph Altman, please.
Good morning. Thank you for the self-contained and impressive presentation. I have one question concerning the user interface. You mentioned that you implemented some kind of awareness. You took the example of the shadow, of the gray shadow, that I have the feeling something else distributed is also working on a sheet or a user interface. Do you have any more concepts concerning how to deal the problem with awareness in such a distributed setting?
So for the very simple thing is that you should see now those pistons and conrods are highlighted, so you see which element is edited by the other persons. You have this view. You can also use some kind of following mode, we said, so that it's more like screen sharing. So this may be useful in the sense of teaching scenarios. You have, of course, the possibility to lock something. So if you say, okay, I'm changing very much or something critical and the other person shouldn't interfere with these changes, you can lock elements. We have, at least for the result visualization things, some kind of virtual pointers where you can highlight and mark things in your diagrams. So these are the basic things we currently integrated, but we are still on the way of thinking on new useful features. And this is also one point we want to gain from the user study. So what is maybe still missing here?
Thank you.
Okay. Another raised hand, Stefan Wenzel, please.
Hello, and thank you very much for your presentation. My question would be, is this planned as a standalone version, or is it planned to implement it into another software in the future? I mean, maybe it's difficult to say at the moment, but the question came to my mind.
Yeah, currently it's more or less a research prototype. It's funded by the Austrian Research Promotion Agency in this so-called Coin-Aufbau program. I don't know if you know it. So we are looking for partners, company partners that are interested in doing some further development. It's more or less now a research prototype which is integrated with this tool from the campus in Wales called Freedyne. Freedyne is publicly available, and at least we want to provide some kind of open source research prototype that can be used for free in the research community. Yeah, and honestly speaking, we have not that big plan now, but we see really large potentials. We are discussing with companies that are thinking in the same way, and yeah, we will see what will be the result in maybe 1 or 2 years.
Thank you very much for answering. Thank you.
Thank you, Stefan. And now I can see John Angelopoulos.
Yes, first of all, I would like to thank you for this very interesting and informative presentation. I would like more or less to make a recommendation, as we have already published a relevant publication in the field of collaborative design based on augmented reality. Under the context of learning factories. It is the research work you present is very interesting. In our paper, we focused more on the visualization of the product itself rather than on the simulation aspect. And I can see that if these two research works were somehow compiled together, the result would be very nice. That's it from my side. Thank you.
So if you could send me a link to the paper, so I would be happy to have a look into it.
Yes, I would like to send you a link. However, I cannot participate in the chat as I am not. It seems I'm not connected. If there is another way to contact you, I would happily to share the paper with you.
I will see if I can type into the. No, there is no chat here. Okay. Yeah, you can find me on the internet. It's my first name dot last name at fh-hagenberg.at.
Okay, thank you. Thank you very much.
Thanks.
Okay, perfect. Very nice, Johannes. You woke up the audience, and that's a good sign.
And now everybody's awake.
Okay, perfect.
Thank you.
Very nice, very interesting. Okay, thank you. We can move to the next paper, to the third paper. The title is High-Quality Sheet Metal Production Using a Model-Based Adaptive Approach. And the speaker is Christian Zehetner from the University of Applied Science, Upper Austria. Please, the floor is yours.
Thank you very much for your introduction. Welcome all in this session. I come from the University of Upper Austria in Wales School of Engineering, and I want to give you some overview of a long-lasting research project. Just let me start my presentation. Now it works. Perfect. So first of all, I want to introduce you in the main topic. It's a bending machine. You can see the sheet is clamped, and with free motion of the tool, we perform the bending processes. We can turn it around and so create complete sheet metal products at the end. So this is the outcome of a long-lasting research project. I will tell you all the challenges and what we have done so far. And finally, we ended up with a digital twin. However, here I will mainly speak about the physical background of the digital twin, about all the simulation models, rather in the field of mechanical engineering, and not so focused on the software implementation. So as I told you, the research project is very old. We started 20 years ago, 2 decades. We used several foundation programs of Austria. And as you can see, we have also several partners. That explains the long list of authors of this paper, the long time, and several partners. And now it's also some time to review what we have done. And one interesting review was that in year 2000, such topics like Industry 4.0, digital twin, and so on, either did not exist yet or were no topic in these fields of industries. And here I observed a very, very impressive change of mind in the way of thinking. And here I completely coincide with the statements of Johannes before. Here we are still in a very interesting progress. So let's have another look on this panel bender. We know the principle, and this company produces panel benders in different types: small machines, larger machines, very large machines, and it's also possible to couple it with sheet metal storage, punching machine, laser cutting machines, and so on. So we can produce metal parts with full automation in very short cycle times. What are our challenges here? First of all, we want to produce with lot size 1. We have very low product tolerances and need very high precision in positioning our tools. So here we speak about the tolerance of micrometers. On the other hand, we have very high forces if we have thick sheets. Here we speak about forces in the order of magnitude of 60 tons. So that causes deformations of the machine in the range of millimeters, and we need a positioning tolerance of micrometers. And another thing is that the low cycle time requirements do not allow us to install a sensor measuring the bending angle and controlling the angle directly. So we need to do this in a feed-forward control strategy to have those low cycle times, and then we also do not know the parameters of the materials exactly. So we need some adaptive concept, and of course this must be real-time capable during this process. The next big challenge is that for these machines there exist many variants, and yeah, we have many options, customer specific requirements. So finally every machine is customer specific, and if we develop such new machine types, we do not have prototypes, machines to make tests. So this development must be done with the virtual prototype. With the digital twin, we use it for creating new machines and also during operation. So here we need a lot of models, simulations, which allow us to be real-time capable during adaptive manufacturing and so on. So the goal was an adaptive digital twin. This digital twin should represent this real production system, all the mechanics. We have plasticity, large deformations, multiple contact, and also should be adaptive. We should be able to react to uncertain parameters of the machine and the sheet, and also be able to adapt changing parameters during working during the lifetime. And this production process should be controlled by the digital twin. And here again, we need information in real time. So let us have a look to our influence variables we know. So first of all, we know several process parameters like the clamping forces, the sheet geometry, bending angle, side length, profile dimensions, and so on. The trajectory of the tool, we can choose it however we like. And here there exist several strategies, for instance, a rolling mode to minimize impressions and also point contact. We also can perform a wide bend as shown here, or a sharp bend. This has an influence on the process forces, of course. And then also the sheet may be equipped with protective films or coatings. And what we also know is the material class. For instance, stainless steel or aluminum. We know the class because the user wants to produce some metal part with a specific material. And moreover, we have an eddy current sensor on the machine, which can identify properties depending on the crystal structure of the metal. And then we have a lot of variables that are uncertain. We do not know them. And here, the most important is the material of the workpiece, of the sheet. We have elastic properties, of course, plastic properties. So for instance, we can describe it with a Holloman flow curve. Here we have stress dependent on strain in an exponential form. A and N are parameters. And it also is necessary to consider the strain rate, the time derivative of strain, because the speed of the forming process is relevant for the stresses too. And then we have to deal with anisotropy, it's rolled steel, and we also have to deal with anisotropic effects. And now, if we consider the materials, we see we have different classes, we know them, but we do not know the specific alloy. And this can be very different. And if we just consider the spread material DC01, we will see that tensile strength shows a very high variation. And if we consider all materials, we have a very, very large range in which these material properties may vary. And then we also have the machine parameters like bearings, tolerances, stiffnesses, friction, thermal effects. All these effects change during lifetime, during a day of working, and so on. So somehow we must be able to identify that all. Then the question arises, should we use model-based or data-driven concept? A very old question. And we know that model-based approaches can be a very large advantage. If we do not have a physical prototype yet, then we do not have data. We need some model. If we create new machines, we must extrapolate and so on. And so this is ideal for the development of new machines. We also have good knowledge from our models. We can use this also as a communication platform, as we have seen in the previous presentation. And we can also use these models for parameter identification. Then we have the data-driven concepts. Here we need a machine to do measurements. This can be also very high effort. We cannot extrapolate, but it's a very powerful tool for machines in operation. And here we can use it for monitoring, predictive maintenance, and yeah, both strategies can be used and are used on these machines, different tasks. And yeah, here in this talk, I will mainly speak about this model-based adaptive concept. So in this project, we have created many simulation models. I want to show you only some examples. For instance, 3D finite elements. We can simulate and model all the details. So for instance, here you can see stress distribution in the machine parts, the elastic deformations with high detail, or also the contact pressure on the sheet. This has an influence on the imprints on the final sheet. So very good for engineering tasks, but computation times of several days and real time, that does not make sense. So we can improve this to reduce complexity by 2D models. We only simulate the cross-section of the machine. The longitudinal effects are considered as an average. And we can see if we compare things like the bending forces, we have a perfect match. That's no problem. And now we can reduce the computation time to several minutes. And we can use these models to study things like perfect trajectories and also special applications like such double bend profiles. But still, we are far away from real time. So what can we do to become real-time capable? We need analytic methods. And here we can use the substructuring method. We can use this for the elastic machine parts, some matrix formulation, combining the displacements with the forces by compliance or stiffness matrix. And this allows us to reduce the degrees of freedom. And for instance, for the displacement, the elastic displacement of the bending tool, we can reduce from 1,000,000 degrees of freedom to only 2 degrees of freedom with the substructure. So that's one thing to model machine parameters. What we can also do is to create a dynamic model of the mechanism, considering all the physics, the inertia, the clearances, the stiffness, friction, and so on. It's also a very lightweight model with some degrees of freedom. And this is also good to consider several machine parameters. But now we need something for the workpiece, for the sheet parameters and all the plasticity, anisotropy, and so on. And here we need also a powerful tool. This very nonlinear behavior, and here it turns out that similarity method can help. Methods helping us to find non-dimensional representation of several effects. Demonstrate it, I want to show you the bending force as a function of the bending angle. 4 materials have been investigated, and depending on the process parameters, we get many different curves for bending forces, high variance for each parameter combination, one curve, and that's very complex. And if we apply such similarity methods, we can find a non-dimensional representation which brings the curves for one material together to one curve, as we see. So the thin red lines are the thin gray lines here, and we can see that for each material we get one specific curve. And that's analytical. So this once reduces the complexity and makes it real-time capable, and we get a very material-specific description. We make the influence of the sheet parameters less complex in our models, and also can use this for the adaptive process, because if we measure forces, compute this scaled representation, we can extract material parameters from that. This feature already is implemented on the machine. The feature is known MAC2.0, version 2, so to say. Here we identify the material, adapt the trajectory, and end up with a correct bending angle and a correct side length finally. So combining all together, all our simulation models and so on, we have a very modularized concept, and the complete workflow of production is also represented in the digital twin. So here our part in this project was were the physical models. The software implementation was part of the company, but from the CAD data of the profile to the computation of the developed sheet, the punching process, the trajectory of the bending process, the clamping and so on, and finally the production, the adaptive production, everything is controlled by this digital twin in real time during this production process. Let me conclude. So one part of this presentation, the major part, was the model-based adaptive strategy we used for many years. We could create a virtual prototype that allows us to develop new machines and variants in short time, customer-specific solutions, and also to use this in the digital twin for production with lot size 1, where very low cycle times. And of course, there's still a lot to do. First of all, still there's a high potential in the simulation models, new generations, more efficient, more powerful, more detailed. This concerns also the parameter identification. And finally, also new generations of concepts, combining model-based and data-driven concepts. So here, from my point of view, there's a very high potential if we combine the model-based concepts where we know a lot of physics and the data-driven concept. So with a low amount of measured data, we could be very successful to increase efficiency and precision of production. Thank you very much, and I'm very excited for your questions.
Okay, perfect. I really thank you, Christian. Very, very nice, very, very interesting and topical. especially. Any questions from the audience? I see the hand of John, but I don't know if it refers to the previous speaker, John Angelopoulos.
Sorry.
Okay.
It is from previously.
Okay. Okay. Don't worry.
Anyway, Christian, very nice presentation. Thank you.
Okay.
Thank you.
Okay. Questions? No? Okay. I have just one question. Do you think that the approach you proposed is domain dependent? We can apply it also in another sector different from sheet metal production or not? Just this.
I think such model-based adaptive strategies can be used everywhere. And of course, we have long times for developing such very precise models for complex processes. And I also think that the future will be some combination to combine these model-based approaches with data-based concepts. And here we also speak about hardware in the loop and so on. If we do not have any hardware, then everything must be model-based, of course. And if we have equipment to do measurements, then of course we should include this. And if we combine it, then we really can get a very efficient approach using the advantages of both those concepts.
Okay, thank you. Perfect. Other questions? No? Okay. Thank you, Christian. Very nice, very interesting. Thank you so much.
Thank you.
Okay, perfect. We can move to the fourth paper, to the last paper of this very interesting session. The title is Equipment Design Optimization Based on Digital Twin under the Framework of Zero Defect Manufacturing. And the speaker is John Angelopoulos. Please, John.
Yes, thank you for the introduction. I don't know if my screen is shared. I believe it's not.
Not yet.
Not yet. Okay.
Now maybe. Okay, perfect. Now we can see it. Perfect.
Okay, very well, thank you. So, thank you once again. I am John Angelopoulos. I work with the Laboratory for Manufacturing Systems and Automation from University of Patras, located in Greece. We'll present you our research work entitled Equipment Design Optimization Based on Digital Twin under the Framework of Zero Defect Manufacturing. This presentation is structured as follows. First, an introduction, a short introduction will be given, then some notes on the state of the art. Moving on, we will discuss about the proposed system architecture, then the practical implementation steps undertaken. The implementation also is evaluated with an experimental case study. Then we conclude with some conclusions, and a future outlook for our research work. So, as we all know, we are currently in the fourth industrial revolution, which besides the digitalization, etc., all the known information, we have an ongoing transformation of the business models. The key aspects are the increased product variety, the tight delivery deadlines, the lot size production, which is independent of the variable demand. We also seek for flexible and reconfigurable manufacturing systems. The reconfigurable side can be expressed as tasks which need no further reprogramming and also require as low as possible intervention from human operators. So according to the Boston Consulting Group, the main driver technologies are summarized on the right side of this slide. We will focus on big data analytics, which is number 9, and cloud technologies, number 7. Moving on the next slide, according to the research work of Lanza et al. In 2019, there is an ongoing transformation of production networks to global production networks, indicating that manufacturing techniques are becoming increasingly digital. Therefore, with this digitalization, with this shift towards this digitalization, the organizations are seeking to find ways to transform their business models. So in this slide, a compilation of the required steps is provided. And let me say very briefly that digital and physical assets have to be interconnected with the use of sensors and actuators. We need data-driven services, which then in turn we will turn new capabilities for advanced services, and finally this will bring us to the desired result, which is monetization, collaboration, and increase the revenues. So according to the European Union, to some European Union statistical measures, we can safely say that 21% of Europe's GDP is coming from manufacturing, providing more than 30 million jobs, and mostly in SMEs, which account for approximately 90% of the total organizations in Europe. So, as a result, we can say that Europe has become a world leader in the industry 4.0. However, in this context, in the context of industry 4.0, there is a new concept, also known as zero defect manufacturing, as it can bring to organizations improve the process efficiency and product quality, while minimizing, eliminating, or compensating defects and process errors. So briefly, the zero defect theory is based on assuring the quality to the customer requirements, to get the manufactured product right at the first time, to measure the quality of the produced assets in financial terms, and we also measure performance based on the accepted standards. So, in slide 6, we can see mainly the motivation for this paper. As we see, modern manufacturers aim to transition their business model to more smart and sustainable ones. Therefore, there is a distinctive movement towards zero defect manufacturing paradigm. So in our paper, we will present a framework, the design and development of a framework, which takes into consideration the customer requirements during the design phase of new equipment. In order to do this, in order to accomplish this, we use digital twin for the simulations, and we are based on historical data gathered from similar machines which are already installed in manufacturing environments. Moving on, in slide 7 and 8, we have gathered some key aspects from the state of the art, where we can see clearly the data-driven approaches. We see also that manufacturing is turning considerably digital and is based on the data analytics. And also we can see a big explosion, if I may say, regarding digital twin approaches. So then in slide 9, you can see a high-level representation of the proposed system architecture. As you can see, the main component is a cloud platform located in the center, which provides 3 basic services regarding the data acquisition, data fusion, and data storage. These services are directly connected to the shop floor level, where we can see the machines and the data acquisition devices installed on each machine. On the lower left side of this figure, we can see the new customer, which who set the machine specifications. In some cases, they provide some data relevant to their production and any other relevant requirements. So we come to the right side of this figure, where the design department of the original equipment manufacturer is located. We can see that the design phase starts. Then we have the integration of data. This combination of information is fed to the digital twin, and based on the design validation, both from the engineering department of the OEM and the customers, we can proceed with the optimization of the equipment, of the designs. So, in slide 10, we present the flowchart. You can see more clearly in a lower level, the steps undertaken. So everything starts from the machine design. The component data are drawn from the cloud database if they are available. If they are not available, they are asked from the user, and they are also uploaded to the cloud database, or else they are also fed to the digital twin. As long as the digital twin has run the simulations, the results are exported and they are evaluated, as said earlier, with the customer and the engineering department. If the design is okay, then we gather the feedback, rerun the whole flow until we reach an acceptable design, which proceeds to the next stage, which is the actual production of the equipment. So, moving on in this slide, some more details about the system implementation are presented. The system implementation is based on the data acquisition device, which is installed on each machine, along with a bundle of sensors. This device is work in a wireless sensor network and feed the data on the cloud database. So for the implementation, we have used the Dassault CATIA CAD suite for the 3D CAD design step. The MATLAB MathWorks MATLAB programming platform for modeling the digital twin, along with the Simulink add-on. Also, the MATLAB has been utilized for the data processing coming from the data acquisition devices in combination with the predictive maintenance library. Also, we used the Visual Studio in order to create the required Python scripts for the data acquisition and handling. For the part where the data acquisition transmits the data through the wireless sensor network to the cloud database. And as we will see in later slides, we use the Unity 3D game engine for the creation of graphical user interfaces. So from a hardware point of view, we are currently using a single PC with the specs displayed there. As far as the simulation times are concerned, we managed to get simulation results for a ball bearing, measuring the frequency, etc., in 3 times and 47 seconds. And in order to create additional data sets for the digital twin based on the Simulink environment, the simulations accounted for approximately 10 minutes and 32 seconds. So given the fact that we have all gathered all the required 3D CAD files for the digital twin and the datasets, complete assembly simulation was recorded at approximately 3 hours. In order to assess our framework, we used the real-life industrial scenario, which derives from a bending machine manufacturer. As stated by the engineers of the industrial partner, they are aiming towards increasing their productivity by 4%. Not only that, but they are also aiming to establish better communication channels with their customers, so that they can provide more customized machines. Besides that, we also use the laboratory-based machine shop, from where we were able to install the data acquisition devices, to test the machines, and most importantly, to gather data and populate the cloud database. What I can say briefly is that so far we have gathered around 1 terabyte of data from all the machines working at the machine shop. So after all this information is processed by the framework, we needed a way to to display this information in an intuitive and understandable way to the engineers. Therefore, we have designed a series of graphical user interfaces. An example of these interfaces is displayed in slide 13. Where we can see at the top of the figure is the main graphical user interface, which consists of a 3D representation or visualization of the design machine. On the left side, there is a tree shape of the assembly. And on the lower portion of this GUI, you can see some meters displaying the selected information. At this point, I have to mention that this GUI can be used for both monitoring the actual machine as well as to see the results from the digital twin of a newly designed machine. Moving on the lower portion of this slide, you can see two additional graphical user interfaces which were designed in order to facilitate the engineering department during the design phase. And for example, on the left GUI, denoted as B, you can see the representation of a typical AC motor, as well as a series of input fields where the engineer inputs the functional requirements of the AC motor. As long as this form has been completed, the data are uploaded to the cloud database, and then they are fed directly to the digital twin in order to run the simulations. The same also applies for the third GUI, denoted as C, where the engineers model a common bearing. So far, we have gathered some initial results. As you can see, the first portion of the figure concerns the time of the design, where we can see that there is a reduction in the design design time. Not on the actual design time, but on the optimization of the new designs, which accounts for approximately 15 days to 1 month, taking into consideration that 12 months will be needed for the design of a new machine. On the right side of this statistical representation, we can see what is equally important, the customer satisfaction and the communication. These results were drawn from mainly from discussions with the engineering department of the industrial partner, where they stated that there is they have noticed an approximate increase in customer satisfaction of around 10%, and the communication between the client and the OEM manufacturer has also increased by approximately 20%. So coming to the conclusions, we have developed a digital twin-based framework for the design optimization of new equipment, manufacturing equipment, taking into consideration the functional requirements of the customers. And in the future, we would like to focus on utilizing simulation networks, more or less this is heading towards the edge computing paradigm in order to be able to reduce the simulation time as much as possible and be able to provide a real-time framework rather than near real-time. And also another important aspect we will focus on in the future is the integration of human digital twins. As we already in our laboratory working with some relevant projects about human digital twins, we think that this is a promising aspect so as to increase mainly the ergonomics of new machines. Concluding my presentation, in slide 16 is some of the key references used for our research work. Thank you. Thank you for your time and your attention.
Thank you, John. Very, very nice, very clear, very precise. Questions from the audience? No questions. I have just one question. Do you think this approach can be applied also in another context different from zero defect manufacturing, or just it is focused just only on zero defect manufacturing? Just a few considerations.
I'm not sure if I understand your question very well. I will tell you this. In slide 6, I hope you can still see my screen, my presentation.
Yes.
Okay.
Oh, yes.
Yes, we hope to lower the costs, lower energy consumption, etc., which are all factors considered under zero defect manufacturing. So I don't really understand how this probably could be implemented under another paradigm. So, could you maybe give me an example?
Oh, I mean, do you think this approach, do you plan to apply this approach also in another context different from zero defect manufacturing in the future? Just a few considerations, if you planned to study also other contexts different from zero defect manufacturing, just this.
Let's say that we are considering also global production networks, as stated in let me see. Yes, in slide 4. Yeah, this could pose also an opportunity to further optimize the designs and facilitate the communication between the clients and the customers and the OEMs.
Okay.
Just let me make a final statement. From our experience so far, we can see that besides all the new technologies and techniques applied so far, which are all welcome, there is still a gap between the communication, the actual communication between the clients and the OEMs. That is our feel.
Okay.
At least in my country, in Greece.
Okay, perfect.
Okay.
Thank you.
Thank
John.
you very much.
Okay. Just a few considerations. My colleagues in the other virtual rooms told me this was the most populated room, the most crowded room in this morning with 50 and 60 people. Then what I mean, this means that this topic is very interesting, and I think that as researchers we need to put a lot of work into these issues. We must push this topic. What can I say is that it was a great pleasure for me to be an improvised chair of this for this really interesting session. The speakers were very good, very interesting, very kind. I also enjoyed the audience. I sincerely thank you for your attention, for your contributions, and I think that we have all learned something today. I think. I hope to meet you in person also in the near future and maybe in the next edition of ISM 2021, and then continue to attend the sessions of this wonderful conference today. And have a nice day and goodbye.
Thank you. Goodbye.
Thank you.
Bye.
Thank you. Bye.
Thank you. Bye-bye.
Bye.
Bye.
Bye.